Hey, in this lecture I want to discuss unique pointer and shared pointer conversion. Now with that I don't mean casting or conversion constructors, I mean can we construct a shared pointer from a unique pointer and vice versa, or assign a shared pointer to a unique pointer and vice versa. We'll actually start this lecture off with a quick exercise, a few tests or experiments that I'd like you to try and do, and I'd like you to note your observations. At this point you should be ready to attempt this exercise based on what we've discussed in previous lectures. So what I'd like you to test and observe is the construction of a shared pointer from a unique pointer and vice versa. Similarly with assignment, go and test assigning a unique pointer to a shared pointer and vice versa. And as a bonus, you can also test the construction and assignment by returning from a factory function that is going to construct and return either unique pointer that you assign or construct to a shared pointer and vice versa. These are basically the things that we will cover in this lecture, but go ahead and try this by yourself as an exercise before we continue. For this example, I have the entity class again. The destructor is going to print out an appropriate message, and then I have a toString and a setMember function as well. Then I have a global function. Remember I talked about factory functions before, so this is going to be unique pointer entity factory. It is going to construct and return a unique pointer, right? And I pass an entity, so that unique pointer is going to manage an entity pointer. And I have some formal parameter with a default argument here, and that parameter is used to initialize the entity that is on the heap, and we use the makeUnique function right here in this return statement to construct the actual entity heap object and return that. In the main function, I'll start off with a few simple examples, and then later on we'll use the factory function. I'll start off by creating this unique pointer, which I'll call UP for unique pointer underscore entity. That is a unique pointer that is going to manage an entity. Let's say we want to create a shared pointer and initialize that to a unique pointer entity. Of course, we are going to get an error, so let's look at that. We'll get a red squiggly, and of course no constructor exists for that. If I try and build that, we will get an error. Similarly, if we try and assign the unique pointer to the shared pointer, we will get an error here. No assignment operator will match those operands. The unique pointer is supposed to be unique, so if you try and assign that to a shared pointer or use that in a copy constructor to construct a shared pointer, then of course you'll get an error, because if you try and do that, then both the shared pointer and the unique pointer will point to that same heap object. So in other words, if that was possible, then both the smart pointers will reference the same heap object, and of course we don't want that with a unique pointer. The unique pointer is supposed to have a unique ownership of some heap object. Nothing else is supposed to reference that heap object. As we've seen with the unique pointer, we can relinquish ownership and we can also move ownership. So let's look at that. I'll do some simple checks and printouts. If the unique pointer is null, then we're going to print out unique pointer as a null pointer. If the shared pointer is not null, then we're going to do the toString function on the heap object that it manages. Let's build around that. The unique pointer is going to be null pointer because we have moved the resource over. We will get 55 printed out with the shared pointer, and then we get end of program. The entity heap object managed by the shared pointer will get allocated, so we get entity destructor invoked. The member was 55. I'll change this if statement to print out something like this. Of course, you can change the if statement to print something out that makes more sense to you. So in this case, I just print out shared pointer, the colon and the space, so we can see, okay, this printout is from a shared pointer. If you remember, with the unique pointer, we have a release member function. And with that, the unique pointer basically relinquishes the ownership of that heap object. So it's going to return the pointer to that, or the address of that. And it will then set the managed pointer of that unique pointer to null pointer. So let's just go and look at that. Actually, I'll use list initialization and this should work now. Okay, so that is going to return a pointer to entity. And we will use that to initialize and construct the shared pointer entity. Build around that. As you can see, we get unique pointer is null pointer now because we have relinquished the ownership. Now that shared pointer is going to manage that heap object, so we get shared pointer 55 because we invoke the toString on the heap object that the shared pointer manages, and then we get entity destructor again, so that works fine. With the shared pointer we have assignments. We can do something like this using the move function, and we pass in the unique pointer entity, and that will also work. We assign that to the shared pointer entity, build around that, and you'll see this will work fine as before. Okay, in the previous section we looked at constructing a shared pointer using a unique pointer and also assigning a unique pointer to a shared pointer. Now in this subsection we will swap those around. For this we're going to focus on the unique pointer, so we'll check if that is pointing to something. If not, we print out unique pointer as null pointer, otherwise we print out here unique pointer, we do toString on that. At this point if you build around we should get null pointer. Unique pointer is null pointer and the entity destruct is going to get invoked. That is currently managed by the shared pointer. If you think about it for a second, constructing a unique pointer from a shared pointer does not make sense because the shared pointer is going to own that heap object and also the unique pointer, and you don't want that with the unique pointer. With the unique pointer again, you only want that instance of the unique pointer to own the heap object. As we can see, if we try and construct a unique pointer from a shared pointer, we will get an error here. Ctrl B to build that, we'll get an error. Remember that the constructors for these smart pointers are explicit. Alright, I'll just go and pick the definition on the shared pointer, for example. And you will see we have an explicit constructor right here. The smart pointer classes also do not define explicit conversion constructors, and in that way we achieve this effect so that we cannot convert in this way. Same thing if we do assignment, we will not have an overloaded assignment operator that matches those two operands, and in that way the compiler will prevent us from assigning a shared pointer to a unique pointer. Move will also not work. Okay, we'll get that cannot convert error again. Of course, if you try really hard, you can introduce bugs and make this do things that it's not supposed to do. So for example, we can use the get member function. I'll invoke the get member function on that shared pointer, and of course that is going to return the address of the heap object that the shared pointer manages, and we use that to construct the unique pointer. This is exactly what we want to avoid with unique pointers. Even though this unique pointer will now own that heap object, the ownership is not unique because the shared pointer also owns that unique pointer. You can think for a second what's going to happen when I build around this. I'll build around the program, and as you can see, we will get a crash. If you think about this for a second, if the unique pointer goes out of scope, it goes and deallocates that heap object. Then the shared pointer goes out of scope. It will try and deallocate the heap object, but it doesn't exist anymore, so you get a crash. As a quick debugging demo, what I'll do is I'll place the breakpoint down here where we have the return statement. And I'll switch over from the locals to the call stack. And I'll right click on here and I'll make sure that I have external code, show external code checked. Okay, so you will see if you check that, that you will get a bunch of extra entries within this call stack. And of course, once we step into this return 0 statement, the main function is going to return the unique pointer and the shared pointer is going to go out of scope. And so it will clean up or deallocate that heap object. So let's look at that. I'll step into this line and you will see this jumps to the destructor of the entity class. And on the stack, this is what we have now. We are not in the main function anymore, so program execution is now within that destructor. And you can actually follow the stack. So right here, it invoked the unique pointer destructor. Then a few other things happen here before we eventually get the destructor invocation for the entity class. Alright, I'll step into that. And at this point, if I bring up the console, you will see entity destruct invoked. Now I'll step into that line again. Of course, at this point, it already destroyed the unique pointer, so it now should destroy the shared pointer. So I'll click on that. And as you can see, it now tries to invoke the destructor for the entity again. In the call stack, we have the main function right here. Program execution has moved from that. You can see the destructor right here for the shared pointer. Then it's going to do the decrement here. You can see decrement ref. Okay, that is the reference count decrement that we get, or the use count decrement. Following the decrement, the reference count is going to be 0, so it's going to invoke the destroy function right here. And because of that, we get the destruct invoked for the entity class, even though that entity is no longer on the heap, we've destroyed it before. And if I step into that again, the program is going to crash. Okay, so I'll just stop that. Moving on, remember we have this unique pointer entity factory, which is going to return a unique pointer using this make unique, alright? And so back in main, I'll just go and clean up here. I'll comment out the shared pointer for now. And then with the unique pointer, I'll go and use the factory function for the construction. And as discussed before, this is going to work fine. This is basically going to do an implicit move constructor. Build around that. And as you can see, this works fine. We get that unique pointer printed out, 55, and we get entity destruct invoked. I'll just remove this breakpoint down here. Next, let's try the same thing with the shared pointer, so I'll copy this here. I can duplicate the code before I change it, but I want to keep things concise here, so I'll just change that to shared pointer entity now. So we're going to check for that, and we're going to print that out in that case. Now, as with the unique pointer, the shared pointer, the statement right here, we are going to initialize it to whatever this function returns. And we're basically going to use a move constructor for that. And as you can see, that works fine. We've looked at construction. Now let's say we want to do assignment. I will change the arguments so we have a different value for the construction. The statement will work fine with the shared pointer. Let's build around that. It will call the destructor for the heap entity that had 55 for its member, and then it will allocate a new entity on the heap with 33 for its member, and then we get shared pointer printed out 33, and following the end of the program we get entity destruct invoked member was 33. With the unique pointer, the statement will also work because again we are using the move assignment operator, not the copy assignment operator. If I do Control K, Control I, we can see the parameters in R value reference, so that is going to be the move assignment operator. If I build around that, you can see the output is basically the same. Of course, I changed it again to be the unique pointer instead of the shared pointer here. It's best to return by unique pointer if you can, because if I go and change that, to keep this concise, I'll just modify this function here to shared pointer entity factory now, and it's going to return a shared pointer, and it's still going to do an implicit move, but of course, as we've seen in previous examples, we will get an error with that, because we have no user-defined conversion, as you can see in these red squigglies that we get here. Of course, this will work with a shared pointer. I'll just uncomment that. And I'll comment the unique pointer out here and the stuff here as well. That'll compile because we are doing an implicit move whether we are doing assignment or construction. So this is why I mentioned with this example that it's best to return by a unique pointer instead of by a shared pointer, because if you do a shared pointer and you try and assign that to construct a unique pointer from that, then again you will get an error. Now this is not something that you'll do all that often, but I'm demonstrating it here in any way just to give you a better understanding of the smart pointer classes. Okay, let's wrap up this lecture. From our discussions throughout this lecture, we saw that we can construct a shared pointer from a unique pointer using a move. We can also assign a unique pointer to a shared pointer using a move. We've also seen that we cannot construct a unique pointer from a shared pointer, and we can also not assign a shared pointer to a unique pointer. Return by a unique pointer instead of by a shared pointer when possible. Okay, based on these observations, and then also you want to keep into consideration what the formal parameter is if it is a unique pointer and a shared pointer, and your understanding of these pointers and what we've discussed in this lecture will help you decide what you need for the formal parameter to solve the particular problem.